Okay, we finally get to the section we've been looking for, the last one. Again, this is for the service core review. There's two cores, by the way, that NATE offers at this point in time. One is in service and one is in installation. And they're different. They're different exams. You want a certification as a serviceman, you need to take the service core and then whatever specialty you want. Heating, air conditioning, heat pump, whatever, or multiple, but there's only one core exam. If you want to have installation certification, then you have to take the installation core and then choose specialties within that, okay, as an installer. Let's go forward, same warnings, if you will. Again, our purpose here, what we're trying to do is get you ready to sit down at this exam and feel confident and capable and get through it with a minimum of aggravation and annoyance. It's progressive, so I hope you're not starting here. If you did, you may want to look back or at least scan parts 1 and 2 to bring you up to speed. Even though a subject, when you're just looking at the frame, the slide, it might look like, oh yeah, I know Ohm's law. But it's how NATE is going to ask you questions about Ohm's law that's important, and maybe the oral part of it might be useful to you. Again, pocket calculator, always important. And again, the user assumes all liabilities. We can't be responsible for misapplied interpretations of what we're saying here today. Let's talk about motors, and specifically motor bearings. Now the bearings are in the center of the end bells, okay? And they wrap around in one fashion or another the shaft. And the shaft is an extension of the rotor in the center. Around the rotor you have the windings, the wiring that create the different magnetic fields, the different poles we're going to talk about a little bit. But the rotor is in the center, and that becomes a temporary magnet in the case of AC circuits, and that responds to those magnetic fields. And an extension of that is the shaft. Now look at this. This is a sleeve bearing, and it's basically a sleeve that's slid over the shaft in the center of the end bell to keep that straight and keep the shaft in the center of the end bell. There are different types of bearings. The two most common are sleeve and ball bearings. Sleeve and ball bearings. And there's also roller bearings. All right, ball bearings can carry a heavier load, axial or radial load. In other words, a real heavy blower wheel or some kind of real heavy large blower system or a big propeller fan or something like that. You're going to need ball bearings. Roller bearings are used for very large motors for belted loads, where you might have 4 or 5 belts on the sheave on the motor relative to the blower. That's roller bearings. So we don't get into a whole lot of that, and the exam doesn't ask you about that. They're concerned about sleeve type bearings and ball bearings. And ball bearings, as you know, have a race, and inside of the race is bearings, small round bearings that rotate with one side of their structure up against the shaft, and it keeps the shaft centered. And because they're constantly rotating, they tend not to wear out, and because they're heavy, dense steel, stainless steel usually, they don't and they're constantly rotating, they can hold that heavy weight that would be on the end of the shaft. How do motors work? Well, you got the stator windings we talked about, and they're talked about stator relative to the rotor because the rotor rotates, it turns. But the stator windings are stable. They don't move. They're just coils of wire. And you know from section 2 that when current flows through a conductor, a motor winding, a magnetic field is set up around that conductor. And if you condense that magnetic field into a small area where you wrap wire around a small tight area, that becomes a very strong, especially if you expose it to iron, that becomes a very strong magnetic field. And motors turn because, and when you hook up to an AC circuit, the circuit is alternating. So what's happening in this stator that's all around the rotor. I'm only showing the top half of it. What happens in that stator is wherever these poles are, wherever these windings are turned, okay, becomes a point of either negative or positive. And as the field changes direction, so does north and south. And a motor rotates because this magnet and this temporary magnet, and this is temporary as long as the current's going through there, that induces a current in here, which creates a magnetic field. So opposites attract each other, and like charges repel each other. That causes the stator and the rotor to continually change direction, and the fact that they're like charges, they're both north or they're both south, repels that. Now remember, by the time this started out north and north, okay, but by the time north gets around here to where south is, that's north again, because of the rotating magnetic field set up in the stator. So that's what causes the motor to turn, very, very basically. All right. Now this is what they call slot windings, where they take the windings and actually put them in slots in the stator to keep them in place. And basically all that is one wire comes in, it's coiled up in one area, and it coiled up in another area. Now we got 4 poles. And you can have as many poles as you have wires. All right, here's a synchronous speed motor with 4 poles. You can take the bell end off and the rotor out and look right inside and see 4 poles. You can count them. All right, that's this. The synchronous speed, I want to define this. The synchronous speed is the speed at which the stator's magnetic field rotates. How often is this north and then south? When this is north, that's south. This is north, that's south. But then it reverses direction. This becomes north-south, and causes that rotor to keep changing. Now, as fast as this field changes, it's as fast as that rotor can turn. So, mathematically, the synchronous speed of the motor is equal to 120, which is a constant, and this is what the constant means. That's not 120 volts. It's 120 is 60 seconds, and this only works in 60 hertz current, is 60 seconds per minute times 2 poles per pole pair. In other words, you can't have a 1-pole motor. The motor would go to that 1 pole and lock up and never move again. You have to have at least 2 poles to cause a difference for that rotor to turn. So 120 represents 60 cycles per second times 2 poles, okay, per pole pair. So 120 never changes. If your frequency is 60, 120 times 60 is 7,200. That never changes. So if we take in this environment in the United States, okay, if we take the number of poles and divide it into 7,200, we get the RPM of the motor. If we have a 2-pole motor, it turns at 3,600 RPM. If we have a 4-pole motor, and we can't have a 3-pole, it has to be 4-pole, we have 1,800 RPM, 4 divided into 7,200. Okay, so how fast does a motor turn? How many poles do you have? Divide that into 7,200. What turns faster, a 4-pole motor or a 2-pole motor? You would think, oh, 4 poles, it probably turns faster. No. Think of it this way. If the motor has to turn, if the rotor has to turn 360 degrees, and you have 2 poles, it only stops twice. It can to the next pole and to the next pole. But if you have 4 poles, it has to start 4 times. Now it's cogging. So it's going to be slower. And in this case, it's going to be half as slow as a 2-pole motor. That's why I showed you all this synchronous speed. They're not going to ask you about this. They're going to ask you about the number of poles. But that's not going to make sense unless you have the other background, at least to most people. 3-phase motors. 3-phase motors are the best starting torque in the universe. Okay? Nothing in our business, HVAC, has better starting torque than 3-phase. And if you want to reverse the direction of a 3-phase motor, you just reverse any 2 leads that feed that motor. And I don't care where you do it, but if you reverse 2 of the legs that feed that motor, it'll go in the opposite direction. then pick any two legs and reverse them again. It'll go in the opposite direction. It'll keep doing that. Capacitor start, capacitor run is the next in order of best starting torque. And that's capacitor start, capacitor run. It has two capacitors in parallel with each other. The next thing in line is PSC, permanent split capacitor. It only has a run capacitor, but that run capacitor, like this run capacitor, is in series with the start winding. And it gives pep to the start winding. Think of it this way. A capacitor is a storage unit. It collects electrons. As long as the voltage keeps rising, that's pushing the electrons into the capacitor, it'll continue to populate its plates with electrons. It'll take all you can give it up to a certain point. Then as soon as the voltage drops off, when you go from, let's say, 120 pure volts to 119, it discharges. So it's a battery for 1/120th of a second. And then it discharges the next 1/120th of a second. All right, that's the way a capacitor works. And what that does is pump the power, the efficiency, however you want to look at it, of that capacitance of that circuit up, of that motor up. Okay, so three-phase, CSCR, PSC. Next in line, split phase, induction motors they call them. Shaded pole. You can grab a hold of a shaded pole motor. This is typically in an attic fan. You know, the old attic fans before they started using capacitor motors. And you can grab a hold of the, you know that as well as I do, the shaft or the blade of the fan when the motor tries to start, and it ain't going to start. It'll just sit there, and if you hold it long enough, you'll let the smoke out of the motor, and then you have to replace the motor. All right? Never let the smoke out. Fan laws. Let's talk about fan laws. Well, the first fan law, and there's a ton of fan laws, and nobody understands them in the field, and everybody says they don't work, they're junk, but that's because of the limiting factors. You can't just apply a fan law. You have to apply at least 3 fan laws, all of which we're going to talk about. And the first one says that airflow rate, CFM, varies directly with the fan blade speed, RPM. So CFM and RPM are the same thing. If you double one, you double the other. If you have the RPM, you'll have the CFM, the flow rate. Okay? Double the RPM, you'll double the flow rate. Oh, so when I have a 1,000 CFM fan, and I want it to be and that's a 2.5 ton fan, and I want it to be a 5 ton fan, all I have to do is double the speed. Yeah. But when you double the speed, you also square the resistance. Square the resistance. The static pressure capability varies as the square of the RPM. This means that if the fan speed, or the CFM, because they're the same, is doubled, the pressure or suction that the fan can develop, or resistance against which the fan can now operate, is 4 times greater. 2, if you're going to double it, that's 2 times 2 is 4. Conversely, if the speed of the fan or the CFM is reduced by 1/2, the static pressure capability of the fan is reduced to 1/4 of its original value. 1/2 times 1/2 is 1/4. Half squared. Now, sounds good so far, right? So I double this 1,000 CFM fan, and it allows me to overcome 4 times the resistance and get 2,000 CFM, right? Now, here's the limiting factor. Power. Power, horsepower, required varies as the cube of the fan speed. This means that the power required to operate the fan is a function of the speed cubed, or to the 3rd power. In practical terms, if the speed of the fan is doubled, or the CFM is doubled, the power required to operate the fan will be 8 times greater. So when and that's the limiting factor right there. How much horsepower do you have? Well, I put in a 1-horse motor, and it was running at 1,000 CFM. I wanted to double it, so I doubled the speed of the fan. You can only double the speed of the fan if the fan can overcome 4 times the resistance and has 8 times the horsepower. that the original fan had. I don't think we carry around 8-speed 1-horse motors in our truck too often. But the fan, these laws work perfectly, beautifully. But you got to understand what your limitations are. In the real world of HVACR, you don't have an 8-speed motor. Okay? And you can't double the speed on any fan you walk up to. I'm leaving out of this commercial stuff, all right? You can't double the speed on most commercial units, 10-ton, 15-ton. You're not going to be able to do that because you're going to create 4 times the static pressure it has to overcome, and you're going to need 8 times more horsepower. Where are you going to get that from? I'm going from half horse to 3/4 horse. I got that covered. Yeah, you got that covered. Conversely, if the fan speed or CFM is reduced by 1/2, the power that is required will be 1/8 of the power. Sure, of course it will. PSC motor facts, permanent split capacitor facts, you should be aware of if you're going to be in the field and you're going to pass this exam. First thing is, if the motor's running capacitor is open, the motor will probably not start. Where is the running capacitor wired? In series with the start winding. How's this unit going to start if you took the start winding out because that capacitor is open? It's no different than disconnecting the start winding from the circuit. These is typically when you go up to a blower motor in a furnace, for instance, and you call for the fan to come on and it sits there and hums. And you grab a hold of the wheel and you give it a little spin and it reluctantly takes off. That's you probably have a bad run capacitor. Unused speed taps on a motor are hot to ground. Okay, that blue wire, that medium speed you're not using, next blower you're on, next furnace blower you're on, doesn't matter. Take a voltmeter, plug it into that blue lead, take the other voltmeter probe and go to ground. Have the fan come on, and you will read a little above or a little below whatever the line voltage power is. Because what you've created is what we call an auto transformer. You have windings, okay, which are wires, coils of wire, in proximity to each other in the motor stator. And if you're using one winding, that's a transformer. You're going to induce a current in the other winding, exactly the way you do in a step-down or step-up transformer. Where do you use step-up transformers? Well, ignition transformers, oil burners. You bring in 120 volts and 10,000 in the output. DC volts, it's rectified, but same difference. Electronic air cleaners, you bring in 120, 240 volts, and you're using somewhere around 5,000 to 8,000 volts DC on those things. It's rectified, four diodes, but it's stepped up. The load, the external static pressure, not the speed tap connection, determines the motor RPM. You don't believe me? Fine. Take a motor out tomorrow, any PSC motor you want, half-horse blower motor, quarter, half, third, okay? Hook it up on low speed, put your mark on the shaft, nothing on it, just the shaft, and tack it. And if the motor is rated for, I'm making up a number, 1100 RPM, it'll draw 1100 RPM. Now put it on high speed and tack it. It's going to draw the same, within plus or minus 1 or 2%. If you draw 1100 in the first case, you're going to draw about 1100 in the second case. You can't change the speed of a motor, PSC motor, until you load it up with a wheel, put it in a housing, put the housing in a distribution system, and close the door. The external static pressure determines how fast that motor is going to run. Just know that for the test. Don't worry about the mechanics of it. That's for your further study. I could spend the next hour talking about that. As the static pressure increases, the amp draw is going to decrease. You know this. When you go to a house and you think you got bad airflow, what do? You take the blower door off and you let the fan run to see if you get more airflow. And of course you will, because you just eliminated all of the return static pressure. You reduced it, and the result is the motor ramped up. You eliminated it so it could turn at a faster RPM and give you more CFM. As the RPM decreases, the CFM decreases. Fan law 1 tells us that. You turn this at a lower speed, you're going to get lower volume of air. No doubt about it, it's a 1-to-1 ratio. You affect this by X, you affect this by X. Affect this by Y, you affect that by Y. Using a replacement motor, this is more for service guys. These 3 values will definitely be asked of you on a test in one way or another. This is general information. Using a replacement motor that is more than one size larger than, and this is in the place of a condenser fan motor, we usually burn the larger motor out because it doesn't see a load. A properly loaded PSC motor, again, this is what we're talking about, has to, if the box says it draws 3 amps, it should never draw 3 amps. If it's drawing 3 amps, it's not loaded. Because remember, the static pressure increases, the amp draw decreases. So if it's drawing 3 amps, it's running too fast. It's not seeing a load. A properly loaded motor should draw, a PSC motor should draw 80 to 85% of what it says on the box. What it says on the box is a red line. You go into a Chevy dealer, buy a new Corvette, and ask the salesman what it red lines at, and he says, I don't know, 8,000 RPM, and you go out in the parking lot, put it in neutral, and put your foot in the carburetor until you're up to 8,000 RPM, would you sit there for a long period of time that way? Don't do that with a blower motor either. Because the motor, the engine in that vet was unloaded, the same as this motor. Well, the amp draw on a PSC motor box or name tag is red line. You should never see that. Even small motors, little induction draft inducer fans that draw 2 amps shouldn't be drawing 2 amps. If they do, you're probably not connected to the flue pipe. All right, connect the flue pipe up. That should drop down 1.8, 1.6, somewhere in there. If it's drawing 2 amps, it's unloaded. It's going to burn up. All right, you're going to let the smoke out of it. Using a replacement condenser fan motor with a different RPM obviously is going to give you head pressure problems. Train, a lot of companies now are using a low RPM fans, 825, to cut down on noise, okay, among other things. And that is going to create, if you take that motor and put it in a place of a motor that used to be 1,000 RPM, your head pressure is going to go through the roof. All right, so just be aware. Replacement run capacitor should be plus or minus 10% of the original. The VAC, the same or the greater. And we'll talk about capacitors a little bit later on. Right now, look at the compressors here. I have 2. I have a regular PSC compressor motor, and I have a CSCR motor. All right, they're both very common. You're going to run across them every day in the field. Some things I want you to notice. All capacitors are wired in parallel with run and start, but they're in series with the start winding, not the run winding. The same here. You've got a start capacitor and a run capacitor, both wired across start and run, but they're both in series with the start winding. Understand that. The potential relay coil on a CSCR motor is wired across start to common. Start to common. They're going to ask you this. The capacitor and the start relay contacts, the start capacitor and the start relay contacts are in series with the start winding of the compressor. Okay? Understand those things about these 2 drawings. You got this, you're going to get by these questions on the test. Duct traverse. All right, you're going to go running out of the room screaming at the end of this one. But it's not that saying, what is this old man telling me? It's not that complicated. You just have to be walked through it. But when you look at the figures for a duct traverse, sometimes it's if it's not meaningful to you, then it doesn't make any sense. And I know that's an oxymoron. If you want to know the CFM, you need to know the cross-sectional area of the duct, outlet, whatever it is, and in square feet, very important, and you're going to multiply that by the velocity. Velocity times the free area in square feet is going to give you the CFM of air that's coming out of that duct. Take an 18 by 10 duct, okay? 18 by 10 is 180 square inches, but we need square feet. So we have to divide it by 144. What's 144? There's 144 square inches in 1 square foot. 12 inches by 12 inches, 12 times 12, 144. So whatever this dimension is, divide it by 144, and that'll give you square feet. In this case, that 18 by 10 duct, and because it's a duct, I don't have to correct for, vanes in a register. I'm right at the end of this duct. I have 1 1/4 square feet of area. Now, if I measure my velocity, I got a velometer, anemometer, whatever I'm using to measure velocity in feet per minute. I go to SMACNA or whatever table I'm going to, or whatever organization I'm going to, and SMACNA publishes excellent tables for this. If you have an 18 by 8 duct, you go in a rectangular section, you go 18 by 8, and it'll say, oh, you got to do it every 3 inches, and you need a total of 6 readings. And this is, when you stick your probe in here, these are the points you're going to read the air velocity at. And because this is a rectangle, you're going to have different readings at different points. You're going to have different reading in the corner that you would right in the middle of the duct. Anyway, look it up in SMACNA. SMACNA says, and I don't know this for sure, but they would say you need 6 points of reading. 6 points you have to read the velocity at. So, this point over here, I read 480. This one was 510, and you add them all up, divide by the number. The total was 3,000. I added them up. I divide by the number of readings I took, which is 6, and I get an arithmetic mean of 500. The CFM is equal to the area times the velocity. What am I going to do? I'm going to multiply 1 1/4 by 500, and I'm going to say, coming out of this duct, or at that point in this ductwork, I have 625 CFM. And I don't have to take the end cap off and open up the duct to do it. I can do all this with a pitot tube. I just make a 1/4 inch hole here, another one there, and I stick the tube in that far, this far, this far, record all the readings, that far, this far, this far, add them up, divide by the number. I got my average velocity. It's an average. So the result of that is I can't have any more than an average CFM if I base it on an average velocity. The only thing that's static here is the 1 1/4 foot of free area we had. But if I multiply that by an average, I get an average number. Understand that. Now the test question is going to be just that. What do you get when you do a duct traverse? Do you get an average velocity? Or do you what's the point of doing it? To get an average velocity or an average CFM? All right, and they're going to have a real funky way of asking that question. But what you're looking for is average CFM based on average velocity. And that's the point I want to make here. But understand this whole process. You have to remember the formula, but know that you need those two values. And it's a simple multiplication. And if you have an anemometer or some kind of a velometer, you can do this in the field. If you want to know what CFM you have in that duct at this point, that's the way you do it. What we have right here. Register. Well, you want to limit the face velocity of the register between 5 and 700 feet a minute. The velocity read right at the face of the register. Either directly on the inside or directly on the outside, but right up against the face of it. If you limit the velocity between 500 and 700 feet a minute, you won't have noise. If it's less than 500, you won't have good projection into the primary, occupied zone. All right? If it's more than, you're going to start getting noise. Grill. You want to limit the face velocity on a return grill to about 400 feet per minute. That will keep this nice and quiet, especially if it's relatively close to the air handler. What's the difference between these two, register and a grill? Well, the grill has no damper or directional thing in the back here. The register does. And it's really not a damper. I hate to refer to that as a damper. It's truly a directional device that causes the air to go down, straight, up. This is not a place to close off, to shut off airflow. because all you're going to do is make small orifices that are going to bleed a high percentage of the air through it under high pressure, because you close this off, you made the pressure behind it higher, under high pressure, which is going to create noise. But everybody calls this a damper, but not for the reason that it is a damper. It's just nomenclature. You think you know how to make a flare, huh? Got the yoke, you got the block, you got the whole thing. What do? Do you drive it in real hard? What do? Well, the proper method is tighten the forming cone into the tubing using an initial 1/2 turn. 1/2 turn of the forming cone, the yoke. Then back off 1/4 a turn, retighten 3/4 of a turn, then back off 1/8. That's how you're supposed to do it, guys. All right, that's the proper way. What's really important here is make sure you ream the damn tubing before you start, or you're not going to have a good flare. Put a little oil on that on the yoke, the forming cone of the yoke. Make sure that it doesn't bind and pull part of the metal, distort it in one direction or another. That's really important. But this is the thing they're going to ask you about. Let's talk about tubing benders real quickly. This is pretty straightforward, whether it's the spring type or it's the lever type. You're going to use these on soft-drawn copper tubing. Soft-drawn copper tubing, both cases. Triangle file, what the heck do you do with that? Well, if you're cutting capillary tubing, and you can see the triangle here, see the sides of this? That's what you use to cut small, real fine capillary tubing. Again, you want to make sure that the tubing end is pointing down. You don't want to get any slag inside the tubing. No different than cutting any other tubing, copper tubing. Never use a hacksaw. The shavings from the hacksaw will end up inside the tubing, and that's going to be a problem. That will jam up orifices internally on your refrigeration system. We just can't afford to have that. So anytime you're cutting regular tubing, you need to use a tubing cutter designed for that. What do fluxes do? Well, basically they prevent reoxidation. When heated, fluxes dissolve surface oxides and protects the cleaned surface from reoxidizing. Transfer heat from the heat source to the joint and removes oxidation products. Allows filler metal to contact and wet the base metal materials. Now, oxidation means anything that combines with oxygen and creates either dirt, because if this surface is not clean, and we're talking about brazing and all that at higher temperatures, if the surface is not completely clean, then you're not going to have a good joint, especially at lower temperatures. Brazing fluxes, and most of you, I know what you're going to say, I don't use flux when I'm brazing, I only use it when I'm soldering. Brazing implies a much higher temperature than solder does, but they do make brazing fluxes. I know they're not commonly used. All right, they're pastes, powders. They fuse at temperatures below those needed to melt the filler metals. And the filler metals in brazing melt upwards somewhere around 1600 degrees Fahrenheit. Because fluxes must be in close contact with the joint surfaces, they are liquid or gaseous at brazing temperatures. That paste or powder you put on becomes a liquid when it's heated up. They remove only surface oxides and tarnish. This is the stuff that will cause you from having a good joint. Other contaminants, oil, grease, lubricating, lacquer, paint, must be removed either mechanically or chemically before brazing. Where do you use this? When brazing copper to brass, you need a brazing flux because of the dissimilar metals. Know also that oxyacetylene, oxygen and acetylene generates, we're talking about brazing, generates higher flame temperatures than acetylene only or LP gas, liquid petroleum gas. Know that when you look at your tanks and you see 2 gauges on each tank, one is tank pressure, the first gauge. The second gauge is the pressure at the hose or the torch, the handle, however you want to look at it. And that's true for both the oxygen and acetylene. Of course, they're different gauges, but they do the same thing. The first one is tank pressure. The second one is torch pressure. All right, that's going to be asked on the test. Of all the flames you can have, we're looking for neutral flame. Oxidizing flame, yellow, noisy, a lot of light, too much oxygen. Carbonizing, dark blue, very quiet flame. You can actually see the carbon coming out of the gas. All right, it actually floats in the air in the form of looks like a black string sometimes. If you have way too much oxygen and not enough air, acetylene. Neutrals, what we're looking for, balanced. OSHA says, Occupational Safety and Health Administration says that if you're going to go up and down a ladder, when ascending or descending a ladder, there's a right way to go up and down a ladder, there's a right way to dig a hole. If you're going up and down a ladder, the user shall face the ladder. Also says, further on, that each employee shall use at least one hand to grasp the ladder when progressing up and or down the ladder. So OSHA says you got to do two things when you're going up and down a ladder. You got to use at least one hand, and you must face the ladder. Now I know that doesn't look real cool, but you got to do it. If you don't do it, the ladder police will wake you up in the middle of the night when you're trying to sleep and take you off the ladder prison. Of course not. It's just for your safety. All right? And you know as well as I do, trying to go up and down a ladder with no hands can be done, but it also can be undone very quickly. Let's talk about refrigeration cylinders. Well, this is what happens if you don't obey the laws, okay? Or you think this is garbage. This is what happens when this stuff is stored at temperatures it shouldn't be stored at. First of all, refrigerant cylinders should be 80% filled with liquid and store only 80%. What do you need? You need this hydrostatic head here available, because as you heat up a fluid, it will expand. What happens to gas? Same thing, except that the gas, the vapor above it, will compress. It will raise the pressure, but it will also compress as the liquid expands. Liquids don't compress, at least not at any value that's going to help us. If this thing was 100% full and you exposed it, let's say, to 140 degree temperature, it would bust the cylinder wide open. That's why every cylinder that holds refrigerant, including your refrigeration systems, has to have some kind of pressure relief device built into it. Anyway, the rule is 80% filled with liquid, so you have a 20% static head, and you don't store it above 125 degrees, which is attic temperature in the summer, temperature inside your van when you're having lunch and the van's locked up in the summertime, probably 140 in the van. The only thing it saves you is this static head. Don't store it above 125. This typically happens around 140 or so. So if this thing is half empty, then you can go way above 140. But, you know, you better know what's in here before you start playing games with the temperature. All refrigerants are heavier than air and will displace oxygen in a confined space, all the refrigerants we use. They're all heavier than air, so if there's a big leak in a small boiler room, you know, don't go low to the ground to get the oxygen like they teach you in a fire. Stand up straight and walk out. That's where, if there's any oxygen left, it'll be up top, not down the bottom. They're heavier than air. They displace oxygen. The DOT, Department of Transportation, is the federal agency with jurisdiction over shipping and labeling of refrigerant cylinders. It's all about keeping firemen safe. When the firemen show up and his truck's on fire, they want to see the bill of lading to know what kind of gas is in there and whether it's explosive, or they look for placards and all that stuff. The DOT, Department of Transportation for the United States of America, is responsible for that. Not the EPA, not UL, not anybody. DOT, Department of Transportation. Definitions. Do you know the difference between an opinion and a fact? You're going to need to know for this test. An opinion is a view or a judgment or appraisal formed in the mind about a particular matter. And it's formed in the mind of the observer. A fact is a thing done. It can't be denied. It's a truth. An opinion, even though I might state it that way, is not a truth. Only facts are truths. Now here, I don't want to mess your head up too much, but listen to this statement. You come up out of the basement. Your hands are all greasy, and you've just been in the bowels of this piece of equipment you're working on. And you say to the lady, lady, I really think this thing is shot, and if we replace it, that should fix the problem. Is that opinion or fact? It's an opinion. I made a judgment. Okay? I made a judgment. I look like this thing is in 1,000 pieces on the floor, but it might be all together. But my judgment was it wasn't working properly, and you need to replace it in order to get it working properly again. The fact would have been, I come up out of the basement and say, lady, the patient died. This furnace has a cracked heat exchanger. You shouldn't use it anymore. It must be replaced. That's a fact. That's a truth. Okay? Understand the difference. Product and services. This is even more difficult sometimes to distinguish. Products and services may be described in terms of their features or benefits. Features. Features, and this is important to know the difference between a feature and a benefit. Features are characteristics such as size, color, horsepower, functionality, design, hours of business, fabric content, and so forth. Those kind of things are features. Benefits answer the question to the customer, what do I get from owning bigger horsepower or bigger size or more colors? What benefit is it to me? Okay, it represents the value to the customer. Because you can talk all along about how you have long business hours, they can always come in and see. Well, the benefit is they can come in and see you if they're working shift work. If you're open when they're off, you know what I mean? That you have more choices for more colors. Those kind of things are benefits from features. Programmable thermostats, here's an example, have a feature that allows you to change the set point temperature, the temperature in the room, in a space according to the schedule of coming and going, your particular schedule of coming and going. That's the feature. It has this setback thing, a setup thing, however you want to look at it. The benefit is that's going to save me money. Because when I'm not there, I don't have to run the heating or air conditioning. I can turn it down to a level that I can recover from quickly without causing me to spend more money. Zoning, when you zone a house, that's the feature. The feature is, we're going to zone this out. The benefit is it's going to be cheaper to operate. And you're not going to put heating in a zone that's unoccupied or cooling in a zone that's unoccupied. That's the benefit. Think in those terms. Thank you for your time and attention. And we will proceed forthwith to the questions. Which of the following would be preferred for a motor directly connected to a heavy blower load? Which of the following is preferred to a motor connected directly to a heavy load? Sleeve bearings, ball bearings, roller bearings, or any of the above? What do you prefer here? I should have said which of the following bearings would be preferred. All right? Ball bearings. Yeah, you got a heavy load, give me a ball bearing. Light load, like just a squirrel cage blower, most of the time sleeve bearings are fine. 2, what is the synchronous speed of a 6-pole motor? 3,600 RPM, 1,800 RPM, 1,200 RPM, 900 RPM. The synchronous speed, by the way, is the unloaded speed. How fast is that shaft turning when it doesn't have a blower wheel on it and it's not under a load in a duct system? Synchronous speed is a theoretical speed. Only because you wouldn't operate it that way or you'd burn it up. Well, synchronous speed is equal to 120 times the frequency divided by the number of poles. You know this part here is 7,200. Divide it by 6. You're going to get 1,200 RPM. That's how fast it's going to turn. Which of the following motors will produce the greater speed? The higher, faster RPM. 2-pole, 4-pole, 6-pole, 8-pole. What do you think? Well, based on the formula you just saw, you got to know it's 2-pole. Which of the following motors has the best starting torque? Capacitor start, induction run, capacitor start, capacitor run, split phase, 3-phase. Which is the best? All-time leading favorite, 3-phase. You don't see capacitors in 3-phase motors, not in our business. There is such a thing, but not in our business. You don't need them. 5. If you double the RPM of a motor, then the CFM will double, halve, square, cube. What happens? It doubles. You betcha. 6. If you double the RPM of a motor, then the static pressure will double, halve, square, cube. What's going to happen if you double the RPM? What's going to happen to the static pressure? It's going to square. Now you got to overcome 2 times the amount of resistance you had to before. 7. If you double the RPM of a motor, then the horsepower requirement will be double, half, square, cube. Got to know this by now. It's going to cube. All right, you're going to need 8 times more. 8. What determines the actual operating RPM of a PSC blower motor? How fast is the actual operating revolutions per minute going to be? The speed tap connections, the system switch on the thermostat, the external static pressure of the system, the room or space demand. External static pressure. The load determines how fast a PSC motor turns, and therefore how many CFM it delivers. What happens to the amp draw of a PSC motor as the external static pressure increases? What happens to the amp draw? Amp draw increases, decreases, amp draw remains the same. This should never be done, as it will do irreparable damage to the motor. Okay? What's the deal here? What's the best answer? Yeah, going to absolutely decrease. Okay? As the resistance increases, the amp draw is going to decrease. No question about it. 10. Run capacitors are wired in series with the run winding, in series with the start winding, in series with the common winding, in series with the start capacitor. Okay? How are the run capacitors wired? Okay? In series with the start winding. They're in parallel with the start capacitors. 11. The coil of a potential relay is wired between start and common, between start and run, between run and common, between run and start, between the run and the start capacitors. Where's that coil put? Yeah, between start and common. Okay, look at the diagram on that earlier slide. Memorize that. 12. The primary reason for performing a duct traverse would be to determine the average velocity of the air in a duct. Is that why you do it? The average volume, CFM, of air in a duct, the cross-sectional free area of the duct, the average resistance, external static pressure of the duct. Why do you perform a duct traverse? So you can find the average volume based on the average velocity multiplied by the cross-sectional area of the duct. 13. The velocity of the air leaving a residential sidewall register should be limited to 800 feet a minute, 600, 400, 200. Yeah, 400 to 600 is a good velocity. Could even go up to 7, but you keep it down to 800, you got noise. Sorry, you got noise. 14. When making a flare on the end of a copper tubing, the forming cone should be moved into the tubing as carefully as possible, as fast as possible, as slowly as possible, in a back and forth motion. I hope you remember that, because I Would have never stopped to consider that. I ream the tubing, I make sure there's some oil on the forming cone, and I don't even know what I do. I guess I just bring it in carefully, and I never thought about back and forth. That's me. I'm doing it wrong too, I guess. 15. Tubing benders should only be used on soft copper tubing, hard copper tubing, random 21-foot lengths of copper tubing, soft malleable tubing. Yeah, soft copper tubing. 16. Which of the following tools should be used to cut capillary tubing, that real small tubing? Aviation snips, often done. Triangle snips, probably the second most common tool. 48 tooth per inch hacksaw, or a 1/2 inch tubing cutter. What should you use? Triangle file. You betcha. 17. A brazing flux is required whenever you are brazing copper to copper, copper to steel, copper to brass, copper to iron. When do you need a brazing flux? Well, you might need it in other cases, but I know you surely need it when you're going copper to brass. I'm not sure you could do copper to iron. Yeah, I don't know. 18. Which of the following produces the higher flame temperature? Acetylene, LP gas, butane, oxyacetylene. Which has the higher flame temperature? Didn't say the lightest to carry around. I said the higher flame temperature. Oxyacetylene. 19. The two gauges on oxygen and acetylene tanks indicate tank pressure and volume, tank volume and hose pressure, tank pressure and outlet pressure, tank pressure and handle flow rate. Yeah, tank pressure and outlet pressure. Number 20, when brazing with oxyacetylene, the flame should be adjusted to be oxidizing, carbonizing, balanced, neutral. What kind of flame do we want? Neutral. 21. OSHA recommends that when climbing a ladder, an employee should always use both hands, use at least one hand, face the ladder, both B and C. You remember this? Yeah, you should. B and C, use at least one hand facing the ladder. You can use both hands, but the requirement, the recommendation from OSHA is that you use at least one hand. 22. Refrigerant cylinders should only be liquid filled to 70% by volume, 80%, 90%. No liquid should ever be in a gas cylinder. What's the answer here? 80% by volume. You betcha. 23. What is the maximum storage temperature for cylinders of refrigerant? Okay, what's the maximum storage temperature? 90 degrees, 100 degrees, 125, 140 degrees Fahrenheit. What is it? Maximum storage temperature. 125. Yep. Can it be in 140? Sure, in the truck. Just don't leave it there all day like that. 24. A big refrigerant leak in a small boiler room will cause the oxygen to be displaced, hydrochloric acid, a fire, phosgene gas. What's going to happen? Now you're going to displace the oxygen. You know that. 25. Which of the following agencies has jurisdiction over the shipping and labeling of refrigerant cylinders? OSHA, UL, DOT, EPA. DOT. 26. An opinion is a fact, a fiction, a judgment, a value. What's an opinion? Might be a value, all right? Especially if you're listening to a preacher preaching brimfire and whatever it is they preach negatively. It's a judgment. An opinion is a judgment. 27. A fact is a truth, brimstone and fire. That's what I was trying to think of. A truth, a judgment, a belief, a standard. What's a fact? A truth. Why isn't it a standard? Well, do you think every standard is a fact? I hope not. All right. It's only relative to the area in question. I mean, the people in Alaska can't make rules in their local code that we would apply in Florida. There's no relevance, Maine to Southern California. All right, that's just a simple standard, and it may or may not have truth and be a fact in the area it's applied. All right, so a fact is a truth. 28. Which of the following is a feature of a product or service? Which of the following is a feature? Saves money, feels good, saves energy, easy to use. Which is a feature? Okay, it's easy to use. That's a feature. That's good. Why is that a feature? It's cool. It's easy to use. 29. Which of the following is a benefit of a product or service? Open late, comes in all colors, saves time, one size fits all. Well, where's the benefit here? Which one of these is the most beneficial? Saves time. One size fits all is a feature. Open late is a feature, not a benefit. I benefit from that if it meets my schedule, so on and so forth. 30. To properly prepare to sit for the NATE exam, one must get a good night's sleep before the exam. Don't come in tired. All right? You know a whole lot more than you think you do. Just by being around. If you've been in business 5 years, there's a lot of osmosis learning, I call it, that's taken place. Just by hearing things, seeing, maybe not understand everything completely, but at least you have an instinctive reaction to it. When you let the smoke out of the motor, you know that's bad immediately. If you were your wife, and let's say she's not associated with HVAC, and she saw smoke come out of the same motor, she might think it was on purpose. It might be a steam machine or some device that produces smoke. All right? So instinctively, you have information. Your instincts are worth nothing if you're tired. B, don't spend too much time on any one question. You've got to answer 150 questions in 4 hours. That's 240 minutes. Do the math. You don't have quite 2 minutes per question. That's a lot of time. You think about the sit down and just watch a clock turn 2 full minutes. That's a long time, but it's not forever. Don't spend too much time. Here's the way you answer, and I've taken a gazillion tests in my lifetime. Sit down, starting question 1, go right through to the end. Answer every question you know cold. Oh, yeah, okay. What color is a red wire? Red, green, yellow, copper. Oh, copper. I know that one. I'm going. And if at any point in time you hit, oh, gee, man, I don't know if it's C or D. I'm really not sure. Skip it. Go on. Don't give it any more attention than that. Because in most tests, at some point in time, that answer might show up in the form of a question. So you won't have to go back and find it. Just leave it blank, skip it, go on to the next one. Just don't get lost in where you are in the answer sheet, because that'll cost you. Don't spend a lot of time. The other thing about spending too much time on one question is it makes you very negative. You get the wrong endorphins working. I go, oh, damn this, I know the answer, I just can't. Don't do that to yourself. Stay positive. And believe me, scientifically proven, the blood flow will be increased to your brain. You'll be able to think better if you don't get negative. C, bring your NATE ID number to the exam. Okay, if you have one. If you don't bring it, of course. And of course, D is all the above. I hope this has been some help to you. That is our fervent hope, that this has been some help to you. That's why we did this. So good luck on the exam. If you need further information, there's a zillion sources you can look at. Online is particularly helpful. If you think I can help you with some clarity, you can go to my website, www.hvactechnicaltraining.com, and in there you will find phone numbers for me and the 2 different offices I have, and email address, and drop me an email. I'm not always sitting by the phone. but I'm not this week, that's for sure. But I will always get back to you if you leave a message or if you contact me by email. I look at those emails every night when I get back to wherever I'm staying. So, again, good luck. Stay well.